Hey everyone. Today I will talk about developing high-performance Node.js add-ons with Rust and NAPI-RS. First of all, let me introduce myself. I'm the creator of the NAPI-RS, and I worked at Vercel Supabase team and ByteDance, LeetCode, and Team Vision before. And I'm now leading the Octobase team at AFFiNE, building the local-first cooperative infrastructure for developers. So recently, we have heard a lot of popular front-end tools are rewriting with Rust, and they are all in the Node.js ecosystem. And as you can see, they are all choosing NAPI-RS. And what is NAPI-RS? First, in simple terms, NAPI-RS is the bridge between Rust and Node.js. And as you can see, all the front-end tools are performance-sensitive libraries, and they are choosing Rust to rewriting their slower JavaScript components and replacing it with Rust. And what's the features does NAPI-RS have? And they cannot resist to choose it. First of all, NAPI-RS allows for very concise syntax to turn a piece of Rust code into a function that can be directly called in the Node.js and JavaScript. Compared to the other Node API frameworks in Rust or other languages, NAPI-RS does not only generate a callable library and binary, but also generate a corresponding d.ts files for TypeScript projects. This is the first big advantage of using NAPI-RS. In the code example on the left, we can see that with just a few lines of Rust code, we can provide a functionality of Rust library UUID to any Node.js caller. And not only it includes the function of UUID v4, but it also provides amazing performance compared to the crypto random UUID provided by Node.js itself. It's about 13 times faster, as you can see the screenshot on the right. So here is a more complex example. Let's pretend we are building a bundler we using NAPI-RS and exposing plugin API to JavaScript here. The bundler function takes a parameter called plugin here, which accepts a string passed by the bundler. We will assume that this string is the source code we want to process with. And the plugin function returns a promise string types here. And let's take a look how NAPI-RS handles this situation. From the implementation of the plugins, we can see that there is TS archetype is used to override the types automatically generated by NAPI-RS. This is because the Rust type system is very different with Rust type system. So NAPI-RS may not be able to generate perfectly TypeScript types automatically. Therefore, there are some APIs for developers. We can declare more precise types using the APIs. In the specific logic, we pretend that the code is the source code that the bundler needs to process and pass it to the plugin API. The call async here means that we are async waiting the return value of the plugin function, so that we will not block the execution of JavaScript here. The biggest magic here is the promise returned from the plugin can be directly awaited in Rust, and here we await the value from the promise and return it to JavaScript side, just like dump bundler do. Returning to the generated d.ts files from AFFiNE, we can see that the async fn in Rust returned a promise value in JavaScript, which means you can also await the async fn in JavaScript directly. Okay, this is a simple example for a dump bundler. So as we can see, we can call the bundler in JavaScript like this. Here is a classical style Node.js callback for plugin API, where the first argument represents whether an error is happened here. And from the screenshot in the right, once we run the JavaScript file, we can get the result from the bundler. Here we pretend we are transform our source code with SWC here and process it async. So now that we have learned about how to develop an NAPI-RS module, it's time to start thinking about how to distribute it. In traditional native add-on solutions, developers may use post-install scripts to compile native code during the installation, or download the pre-compiled binaries from CDN or GitHub release. You may have gone crazy dealing with various post-install scripts failures when using another native add-ons. One of the best features of NAPI-RS is out-of-box pre-compiled and distribution solution with 0 post-install scripts, which is especially convenient for GitHub Actions users. Of course, NAPI-RS also has other advantages, such as compatible with serverless environments, such as Vercel or Netlify. In terms of pre-compile, NAPI-RS maintains a complex toolchain that supports most of mainstream platforms on the market. In this big table, you can see which shows the NAPI-RS can pre-compile add-ons for particular platforms on which Node.js can run. In addition to the multi-platform pre-compiled solutions provided by GitHub Actions, NAPI-RS also offers cross-platform compilation solutions for other CI platforms like CycleCI or GitLab CI. You can use NAPI-RS CLI to compile binaries for the following platforms only on Linux and macOS. And it's really easy to integrate into your own CI scripts and your workflow. Okay, up until now we have been talking about the advantages of using NAPI-RS, but if it had no drawback, why haven't I rewritten all the packages on npm using NAPI-RS? So now I will discuss some of the trade-offs using NAPI-RS or similar technologies. It's including the following points. The first is cross-boundary overhead. We all know the Rust is very fast language compared to JavaScript, but you may not know there are many core overhead if you're calling a Rust function from JavaScript. So I will talk about it later. And the second one is trusting. And the final one is debugging. Let's start from the cross-boundary core overhead. Contrary to making complex tasks, this table shows making Rust to do a simple calculations and wrapping them with different Rust NAPI frameworks, then comparing them to pure JavaScript with the performance. You can see that in the simple computation, JavaScript can be several tens to hundreds of times faster than Rust. But why is the case? Hell, shouldn't Rust be much faster than JavaScript? Actually, it was cross-boundary core overhead I mentioned about. Cross-boundary core overhead refers to the performance cost occurs when making function calls between different binaries and languages. In the case of Node.js and Rust add-ons, they are compiled to separate binaries. You know, Node.js is a single executable binaries, and your add-ons is another dynamic linked library. So traditional native language compiler optimization technologies such as LTO and PGO and such things do not work when making a cross-binary function calls. Secondly, the function call cross the JavaScript engine. So there is a lot of additional work to make to be done during the core, resulting in more performance overhead. As we can see in the sum function in the right section, in addition to the necessary A plus B operation, there are 5 additional Node API calls compared to the pure JavaScript implementation, which are used to handle, type conversion and different for the different runtime and the language. And the cross-boundary calls also cause another issues. In this example, the pure JavaScript implementation has the opportunity to be deeply optimized by the JavaScript engine like V8. But however, in the implementation on the right, the inserted native add-on function may cause the entire some hot path function to be abandoned by the engine for optimization. So this will introduce more overhead here. And the second trade-off is trusting. There have been more and more news about attackers using NPM to distribute their codes to steal secrets from developers and users. So using NAPI-RS or the other native language to publish native add-ons to NPM will increase the will exacerbate this issue, as the released binary cannot be effectively added by the tools like however, this situation has recently improved as the NPM officially released the provenance feature for sign published NPM packages, preventing them from being tampered with during the publishing process. Okay, the third overhead here is the debugging. In order to reduce installation size, most NAPI-RS packages just drop their debug symbols during the release, and the screenshot here is from the issues on the official RSpec repo, which shows that when issue or panic happens, the error stack cannot be displayed at all because the debug symbols was removed during the publish, making it much more difficult to locate and fix the problem on the developer side. To solve this problem, NAPI-RS will provide a debug symbols download feature in the next major release to reduce this problem. And if you want, and you can download the removed debug symbols again if the panic happen on the developer machine. Okay, so conclusion is NAPI-RS is very easy to use and provides an end-to-end solution from development and deployment. And NAPI-RS can improve Node.js performance progressively, and not all scenarios are suitable for developing with NAPI-RS and Rust. So that's all. Thanks. Any questions?
I have one question. So, like, given all the overheads that you mentioned, how do you weigh the trade-offs between like when to optimize some part of your like JavaScript code and switch it over to use Rust? Yeah.
It depends because even I have written thousands of NAPI-RS libraries, but I can't give an answer that which parts of your application can be rewritten by Rust, because it needs to be profiled, and as you can see, the Rust codes may, for example, 10 times faster by JavaScript compared with JavaScript, but it could introduce more overhead, like de-optimize your JIT in Node.js or some other overhead we can't see in pure JavaScript application. So the only way to do that is rewrite small pieces, which introduce less core overhead, like less Node API calls, and profile it progressively and see if we can get a better result of performance.
Can you give an example that your NAPI-RS package is significantly faster than your Node.js implementation?
Yes, maybe RSpec is a great example. RSpec is a library which has the same API with Webpack. It has the same API and the same configuration and the same features, but it's 10 or 20 times faster than Webpack in boundary. Yeah.
And it is built with NAPI-RS.
Yeah.
I heard it was 5 to 10 times. You said 10 to 20 times.
It depends on projects. Yeah. If you are using like less loaders and if you are using more JavaScript written loaders and the plugins, it will be more slower. But if you are using the built-in functions like TS transpile or CSS transpile, it will be much more faster.
Is the AFFiNE backend written in Rust?
We don't have a backend server right now, but we have a universal infrastructure for cooperative and real-time cooperative, and it's written by Rust. And in our election client, part of the data processed layer is rewriting by Rust and NAPI-RS to replace the JavaScript version. Yeah.
I'm curious, if you want to use Rust on the backend, why did you choose to build on Node and do that library instead of going with Eno, which is basically
Yeah.
then you could skip the C API.
Yeah, it's a good question. We have tried to build our business codes on Rust before, like CRUD business code, and it's really non-productive for engineers because it has a very complex type system and borrow check, and we can't ship our features before it changes. Yeah. So in most cases, I think Node.js and JavaScript and is more suitable for this business. But in other scenario, like AI, like our business model, like cooperative and real-time for real-time performance sensitive scenario, we need to replace the part of Node.js application with the Rust. Okay, any other questions?
By the way, if you ask questions, we will have swag for you. T-shirt, yeah.
Here.
Can I have some swag?
We see that your API-RS are going to do some preview for the matrix of the supported OS and architecture, right?
Yeah.
So what will happen if the user is using some new architecture that you don't know? What would happen?
You can still compile your own binary if you want. It's not a conflict with the pre-compiled version.
That's the post-install script?
Yeah.
Okay.
but for the mainstream OS and platform, it's not necessary. Yeah. Okay.
Actually, I have a question for when you are thinking about like using Rust to write a NAPI-RS. Is there any thoughts that you might want to use Zig? I think how do you compare the performance between like Zig and Rust when you are writing like the build or
You mean Zig? Ziglang?
yeah.
From my knowledge, Zig is a fancy C. It need to manage your own memory by hand. So if you go into the bound.js issues, you can see many a lot of segmentation faults and panic issues here because of this. But Rust is different. It has borrow checking and it will manage your memory automatically. So it's more memory safe in this way. And I think it's more convenient and trustable for the infrastructure. Yeah. Okay, I think.
Awesome. Yes. One more round of applause for Brooklyn.
Thank you.